Chapter 6 is called Descriptive Statistics. There's actually value to Chapter 6 in two ways. First, Chapter 6 is going to teach us the difference between a population and a sample. And it's also going to show us how to make frequency diagrams, or specifically histograms, which help us learn about the data that we are actually analyzing. So first, we're going to start out with the part of chapter 6 that teaches us about the difference between a population and a sample. So when we're talking about data, we're talking about observations that we actually collect numerical values for, or it shouldn't have to be just numerical values, could be anything. But when we say a population, and that's what the first fill in here is, population. We're talking about every possible value that has existed, currently exists, or will exist. And this can be for finite data or infinite data. It could be an infinite population. It can be continuous. It can be discrete. A portion of this population that we take for an analysis is called a random sample. And by random, we just mean that we don't include any bias when we grab the data, because sometimes you can have data that are related, so you want it to be purely random. The expected value of a population, so you know this from previous chapters when we refer to it as capital E and then a capital X on the as the argument there, the expected value of a population is called the mean, or what you'll often see me refer to it, mu, I refer to it as the population mean. And the average of a sample, not the expected value, but the average of a sample is referred to as the sample mean. And we denote that as a lowercase x bar if it's an actual value, but it turns out it can also be an uppercase x bar if it is a random variable, which we'll see happening in the next chapter. A measure of the spread of a population, and you already know this, we call it the variance. You've seen that a few times. And I also often refer to this as the population variance. Now, the book will, when they say mean and variance, they are talking mu and sigma squared. Whenever you see, though, however, the word sample in the sentence along with mean, they're talking about x bar, and they're also talking about the sample variance down here, which is s squared. So there is a difference between sigma squared and s squared, and between mu and x bar. So that's an important point. We also refer to S is the sample standard deviation. Okay, I think that's all I wanted to say about that slide. Oh, you can also have, this is also a numerical value. This is a numerical value, but can also have capital S and S squared and capital S for the sample standard deviation. These are random variables. And again, we'll get to that when we get to the next chapter. Okay. So now, what is the difference between a population mean and a sample mean? So if we had a finite sample, it doesn't have to be finite. This is just an example of it. Notice what the formula is here. And I'm going to use two different colors here. I'm going to use purple or purple-ish, yeah, when I'm talking about a sample, or a population, and I'm going to use blue when I'm talking about the sample. So the population mean here, notice that we have a capital N here and a capital N here. That means that N is the total number of values in our finite population. This, again, I refer to, this is called the population mean, or just the mean as the book writes it. it is a Greek letter. So whenever you see the Greek letters, you've got population in general. Whenever you see, regular letters like this, we've got a sample. Now for a random sample of size n. Now what is n? N is, say I took a sample of 10 items from a population of, say, 1,000 items. Little n is always going to be smaller than big N, okay? And the formula for that is almost the same, right? Except the only difference is instead of going from 1 to capital N, we're going from 1 to lowercase n. Again, this is the sample mean. And X bar, and again, this is a numerical value, it's not a random variable. X bar estimates, it's considered to be what we call an unbiased estimator of our population mean mu, because we often don't know what mu is. In fact, we usually don't know what mu is. You couldn't possibly have all of the values of a population. It's almost impossible to get that, especially in manufacturing or in an applied setting. Okay, so how do we get population variance and sample variance? What's the difference between those two? Well, again, I'm going to use purple here for population. And sometimes we refer to this as the variance of our random variable x. Let me go back one slide here. I also wanted to point this out. When we're talking about population mean, we also refer to that as the expected value of x also. You already knew that anyway. Okay, so we have the variance of x, sigma squared, and the way we get that is we take every single value in our population, so these are population values, we sum them up, we subtract our population mean, we square it, and then we divide by, again, this capital N. And again, I'm going to call this is called the population variance. And the easiest way, I don't prefer this formula, so I'd like you to use this formula. If you need to get the variance of any x, whether it's discrete or continuous, or whether it is, well, here in this case, it would be discrete. This works, by the way. It's the expected value of x squared, and you already know this from previous chapters, minus the mean squared. So again, a reminder that this is the best formula to use if you have to compute the variance of a random variable. And if I wanted to get the population standard deviation, sigma is the population standard deviation, and we already know that we can get that just by taking the square root of the population variance. Now, if I have, again, my sample size, which is n, something smaller than the number of items in my population, this is how I get the sample variance. So this is what we call the sample variance. And again, we're going to sum from 1 only up to the number of items in our sample. We take each of the values in our sample, subtract the sample mean from the previous slide, and that's how we get the sample variance. And again, we have s squared estimates the population variance, sigma squared. And if I wanted to get s is the sample standard deviation, and S estimates our population standard deviation right there. So that is the difference between population variance and sample variance. Previous slide is the difference between population mean and sample mean. So now, if you wanted to do some computations here, and I always like to do examples, you probably figured that out right now. Suppose that I took a production run of well over 18,000 connectors, all right? So we know that my population, we know that N, the number of connectors, is definitely bigger than 18,000. So we're going to take, though, a sample here of 8. So my sample size is going to be 8. And it says, compute the sample mean and sample standard deviation. Okay, so if I want to get the sample mean here, you've done this 100,000 times in your life, I'm sure, but here are my eight connectors with the pull force data recorded in PSI. So how would I get that? Pretty easy, right? I'm going to take each one of those values, 12.6 plus the second value would be 12.9 plus, and then the last value, I'm going to take 8 values here for the numerator, and I am going to add them together. So my last value will be 13.1. And then I'm certainly going to divide by 8. This is like, something you've done many, many years ago. What I end up with, it works out to be exactly 13.0 PSI. So that's my sample mean. If I want to do the sample standard deviation, this is how I do it. Again, n is equal to 8. So I would take each one of my values. So my first term in the numerator will be 12.6 minus 13 x bar, and then I'm going to square that, plus, and then I'm going to do that for each one of these terms so that my last term will be 13.1 minus 13 squared. That's the numerator. Then I'm going to divide here by n minus 1, and we'll talk about that a little bit later while we divide by n minus 1. When I do that, what I find out is that s squared works out to be 0.2286 if I go to 4 decimal places, and that is PSI squared. If I wanted to find the sample standard deviation, I would just take the square root of that, and that works out to be 0.4781, and now the units are just in PSI because I took the square root. Now, I want to point this out too. So this up here, this would be considered x1, this is x2, get the idea here, dot, dot, dot. And then this would be x8. Now, there is a function in your calculator that might be very helpful to you. If you have a lot of data and you just want to compute the sample variance or the sample standard deviation or the sample mean, and you definitely have homework that asks you to do all of that. If I want to use my calculator, I will go to, so this is my TI series, at least 84 or 83. I'm going to go to the function called stat, and then I'm going to go to calc, and then I'm going to go to one variable, and then it says stats or statistics, and then you can figure out what the mean and the standard deviation are. What I want to do is grab my calculator, which I forgot. So hang on one second. I hope this shows on the video. Let's see here. Got a couple of them, and sometimes they don't show very well. This might not work. Let me see here. Let's see if I can pause this. I don't think I can pause this. Oh, I guess not. Okay, well, we're going to do it this way, and hopefully you can see it. Let me get down here tight on it. Maybe this will work. Let's see here. Let me clear it out. So if I went to stat right here, and then sorry about this. Here we go. This might actually work. Okay, here we go. So if I go to, you can kind of see that it says edit and calc, and there we go. Here we go. So I'm so sorry, I should have tested this ahead of time. Now we go to stat, edit, and then I've got my my list functions here. I know this is blurry, but I'm going to clear those out. So if I go up and I highlight L2, for example, and then I'm going to hit the clear key and then enter, and then I'll go over here to list 1, clear key and enter. Then I can put this data into this list 1. So that would be 12.6, 12.9, 13.4, 12.3, 13.6, 13.5, 12.6, and 13.1. Hopefully I didn't make any mistakes there. But when I hit the stat key, let me see if I can show you here. The stat key is here. And then I'm going to go to scroll over here to, it says edit, then it says calc right there. And then the very first option under calc right there is one variable statistics. Again, I'm sorry that this is blurry. I will direct it to list one. So I'll do second function and then list one. And then I'll hit calculate. And what you'll notice here is that it gives me, a little hard to see, but X bar is 13, and it says S sub X is 0.4781, and sigma X is 0.4472. So since this isn't showing very well, but I did want to point out how to use this function here, I would like to point out something that is important to remember, and that is that when we are, there we go. When we're using those functions in the calculator, this is what you're going to want from the calculator. When the calculator says S sub X is my sample standard deviation, it will also give you sigma sub X, and that would be the population standard deviation only if the data are the population. So if this was the only 8 values of the thing, of the connectors, if we only had 8 connectors in the whole wide world ever, then we would want to use this as the standard deviation of my population. But since it's a sample of 8 from something bigger than 18,000, I'm going to use S sub X. What the TI series will also do is they will always show you X bar, and that is actually the sample standard deviation, but X bar also is mu, again, if, I'm sorry for cluttering this up, if the data are the population. So from this day forward, what you're going to be doing if you ever use this stat calc one variable statistics function is you're only going to be using it for X bar and for S. So that's an important point, and that will help you with the homework. A couple of other points that are important to note, and that would be, let me use a different color here, is that the sample, I'm going to do it up here. The sample standard deviation or sample variance is always going to be bigger than the population variance, because when my sample is bigger than 1, and my sample standard deviation thus would be bigger than sigma itself. So that's just something kind of to note. Okay, so now, why is it that when we're computing the sample variance that we divide by n minus 1 and not just n? And it's actually an explanation that is difficult to to give you right now because it's beyond the scope of the course. So let me just kind of point out the differences and give you a general sense of why that is. First of all, the population variance, and again, I'm using purple for population variance, sigma squared, is based on data deviations from the population mean, right? So this is that, and we've got population capital N, like that. So that's my population. Okay, from the population mean, where N is the number in the population, if it's a finite population. Now the sample variance, which is S squared, is based on the data deviations from the sample mean, which is X bar, not on the population mean, mu. Remember that X bar is an estimator of mu. It's close, but it's not exactly the same. So what you see here is the differences is you've got population variance, sample variance, number in the population, number in the sample, and the number in the sample is that lowercase n here. But again, I said, well, why are we dividing by n minus 1? Why don't we just divide by lowercase n? The problem is it compensates for the error in the mean estimation. So we will always be referring to n minus 1 is called the degrees of freedom. And what it does is, that's the general definition of it. The n-1 divisor compensates for the error in the mean estimation. If you know anything about bias, it also creates an unbiased estimator, but we don't get into that in this course. Okay, so that is the difference between population and sample, population mean, sample mean, population variance, sample variance, population standard deviation, sample standard deviation. Now we're going to go into the second part of chapter 6 that is important, that has nothing to do with what I just said. And that is, what is a histogram? So a histogram is just a bar chart. You've been making them for a while, probably even in elementary school. But I'm going to refer to the values in these intervals as bins. So basically, I'm going to take the data and I'm going to be chucking them into bins. The shape of a histogram can actually tell us what probability distribution the data might be from. Not necessarily, but might be. Now, this is the book's recommendation for how many bins you should have in your bar chart or in your histogram. And the rule of thumb is as follows, that the number of bins in a histogram should be close to the square root of the sample size n. So in other words, I could have written it this: number of bins should be about the square root of the number in my sample. We also like the width of each bin to be the same, but it doesn't necessarily have to be. So again, this is a rule of thumb. It's not required, but in exams and what's required here? And homework and such, you will be expected to know what the rule of thumb is and to be able to apply it if you are asked to do so. Okay, so here's some examples here. A histogram, shape, and terms, all right? So I've got quite a few examples here. I think this will be very helpful. When we see that a histogram, again, is a bar chart, we would call this a negative or a left skew. We also sometimes call it a left skew or a left tail. This is a symmetric one because it looks the same on both sides if I, divided it down the middle here. And then we can have a positive or right skew or right tail. So that's what histograms typically look like. Again, a histogram, this is on the previous slide, but I want to remind you of why we do it. A histogram can tell us what distribution the data may belong to. I'll put it here, belong to here. So for example, and I'll just jump right down here, if I had a histogram that looks like this, and again, the y-axis, that would be what we would call the frequency or the number of observations. This would be the x-axis here. It looks pretty symmetric and much like from chapter 4, a normal distribution. So if we had a histogram like this, we could say that my data, my random variable x, may be from a normal PDF. Okay, that is if it's continuous data, of course. Here is another example right here. If this y-axis is the frequency and this is x, and my bars seem to be doing this sort of exponential decay, then we could say that my random variable x may be from an exponential distribution because it fits that look, right? Here's a couple of others. Suppose that I had, now notice they're kind of the same here. They're both x on the x-axis, both frequency on the y-axis here. But suppose if this was discrete data, which is usually whole numbers, and if this is continuous data, then each one of these indicates that the data may be from, for example here, x may be discrete uniform, from a discrete uniform PMF, because that would be discrete. And here, my random variable may be from a continuous uniform PDF. That would be from chapter 4. So that's what we use histograms for, and super useful, and works out a lot of the time. So let's make a histogram. Here is the example that's in the textbook. I like this one a lot because making a histogram isn't necessarily, sometimes you can take some liberties with the width of the bins and with also, the width of the bins and what the values on the endpoints of the bins are. So this is a good example, for example. So here we go. We've got 80 pieces of data here. So my sample size is 80 of these alloys, and they're looking at the compressive strength. Again, it's a PSI problem. We've got 80. If I look for my lowest value here, the lowest value happens to be 76. It's right here. And if I look for my highest value, that happens to be 245. So the range of this data is 169. Now, if I take the square root of 80, that's approximately 9. You could do 8 or 9. I like 9. It's closer to the square root of 9. So if I wanted 9 bins over a range of 169, it might just be more convenient to round that up to 180 and then make each bin to be 20 psi in width. So that's what they're going to do. So they're going to say, okay, we will start instead of going from 76 to 245. What they're going to do is they will go from 70 up to whatever the last value is, and you'll see what that looks like. But that means that if I take a range of 180 and divide by 9 bins, I'm going to have each bin is going to be 20 psi in width. All right. So another point I want to make out to you here is, even though these are whole numbers, this is actually continuous data. So a little asterisk here. This is continuous data. Even though we have whole numbers, they've just rounded it to the nearest whole number. So just because, I probably said this before, just because a value is rounded to an integer does not mean the data becomes discrete. So that means that the data does not necessarily become discrete, and I wanted to point that out. So this is still continuous data. Okay, so how would we do this histogram? We would do this histogram as follows. Remember, we said they would be 20 apart. Here's my lower value. Here's my higher value. They've decided to start at 70. So they went from 70 to 90, 90 to 110. And notice that we don't want to double count. So we've got less than or equal to on this side of the inequality and less than here. You could do it the other way too. You could have started out with less than or equal to and less than or equal to, and then had this be the less than or equal to. The point is you want to use the inequality so that you don't double count the values. So if we went up here into this data set, what we would find is that there are 2 values that lie in this range. And then we would make a bar chart here. So here we have the compressive strength. Here we have the frequency. We're making our histogram. Again, my number of bins is 9. If we go up here and count, we'll see that there are 3 values in the next bin. We'll see that there are 6 in the next, and so on. And I like to write the number of observations above the bars in my bar chart: 10, 4, and 2. Make sure it all adds up to 80. And what we notice about this histogram is that it looks very symmetric, right? So I could have done something like this, and I would say that the data appear to be from a normal PDF. And once we know that, what we could do is we could figure out the sample mean and the sample standard deviation and actually do some probability computations with that. Okay, so that's how you would make a histogram. When you're doing the homework, make sure, I don't like the way the homework problems are, but I gave you a couple of them anyway. They're going to ask you which of the histograms fits the data that they give you. That one you're probably going to have to reverse engineer. In other words, look at the picture of the histogram and then create this. I don't like the way they presented it, but that's the way it is. So you might have to reverse engineer it, and it's a multiple choice question for both of them. So if you have any problems, put it on the discussion board and I will happily answer that for you. All right, the next thing we need to talk about is something called a Pareto chart. A Pareto chart is also a bar chart, but the x-axis is not actually values, it's categorical. So if I looked at the number of airplanes in 1985, this is from the textbook, that Boeing produced, we saw that we had the 737 series, 757, 747, 767, 707. Notice just because these are numbers, they're not really being used as numbers. These are labels, and it's categorical. And a Pareto chart always, always, always has the highest bar here and the lowest bar here. So it always goes down in decreasing order. That's what a Pareto chart is. It's used a lot in quality control applications because what it does is it permits you to decide where to, where the biggest bang for the buck might be if you wanted to put some efforts into improving things. So here endeth the lecture about chapter 6. Again, sorry about my calculator here. I'm going to get my other one for future videos and see if it works out a little bit better.